Ladies and gentlemen, I present to you a quantum computer on the edge of my bed that is working in room temperature, 16 dimensions, and 4 qubits. And not only that, but I accidentally touched it and it created a neurological link pathway, and it actually changed my brain structure just a little bit. I felt it. It was kind of awesome. So, and here's the output. 16 bits of information, or 16, not bits, 16 variables of information. You can see it in the amplitudes, and I'll explain that later. So they're made of, each qubit is made out of 3 MJL 21194G transistors, which are hard to get. And I'm Michael Ellis, by the way, which are hard to get. And that's a joke. And going on, which are hard to get, and they're really good at withstanding static electricity and high voltage inputs. So they're really cool if you happen to be in a nuclear war or something like that, and stuff like that. So I don't know, I kind of like them for that reason, because they can withstand a lot of stress, like hence being on the edge of my bed and being all staticky. So anyways, I'm just there for convenient purposes, being next to my orgone bucket antenna and the battery bank I conveniently have right there for no apparent reason. And so yeah, so they're all linked in series. They all are H gates, which means they are 2 inputs going into superposition and generating 2 outputs, which are the same actually for some reason. And because they're superposition, it's just a superposition state that you're measuring and drawing off. There's 2 lines though, but they're all the same, both the same, because it's just a comparison of 2 variables. And you're drawing it off and putting it through another one and another one and another one, and then you get to the end, which is the 4th qubit, and you draw off the measurement, which, by the way, doesn't interfere with the operation of the qubits. You can still get a changing output if you happen to interfere with the circuit in any way, like touching stuff randomly. It'll actually change the output, like the amplitude and stuff. So if you change anything in the circuit, it'll change the output, and you'll still be able to measure it, even if you don't disconnect it. So that's kind of cool. So these are like the ultimate wet dream of the quantum physicist, because they're room temperature conductors, superconductors, squids basically, kind of like the D-wave stuff, but they're made out of transistors instead of magnetic stuff, or whatever they use. I don't know. And they happen to be room temperature operational. And not only that, but they're made from common transistors, not the high-tech stuff that they're using, or like the single atom transistors or the magnetic spin state crap. And they happen to be accessible to mankind instead of being stuck away in vaults by super elite people and big tech companies and all that other BS that is so secretive and elite and inaccessible and high-tech that you can't even get your hands on it to study it or use it, besides the little player thing that they put in websites that is just to get you interested in it and to buy into their crap and believe that they're gods and stuff. So anyways, I'm getting too diverted. So anyways, here goes, and here's the output. This is a 16 variable output. This has 16 amplitudes or points of interest, or 16 spin states, if you happen to be interested or not spin states, energy levels. We're talking energy levels here. We're talking atomic energy levels. 16 variables, 16 amplitudes, 16 frequencies riding on a 60 hertz wave that's just pure noise, or the beat of the ether, if you will. And they're all there and they're all riding on the 60 hertz wave, and you're getting those amplitudes directly into your oscilloscope with one wire and nothing else, just your probe, old-fashioned electronic probe on an oscilloscope, and you're getting that directly out, no frills, none of that microwave or RF stuff that the other super wired and protected and shielded and cryogenically frozen supercomputers need. This is just simple, bare bones, salt of the earth stuff, and you get it right here on the readout as an amplitude and frequency, and you can measure it and scale it and manipulate it and look at it, and you get it on your oscilloscope that you bought for $200 from Amazon. You know, it's not, this whole computer costs like $10 to build. I'm not kidding you. Like, probably including the wires. So it's that inexpensive. And the battery I had anyways, and I just needed some solder to put it together and some wires to put it to contact the stuff. But I mean, if you bend the leads off of it together, you can solder it together into a neat little package like I did here. And with that one, with that one, you can solder it together into a little cube thing of 3 transistors with the leads all soldered together and coming off, if you're smart about it, which I actually figured out finally how to do that. And without bending and breaking the leads because they're so sensitive and breakable. But I mean, you can build this for like $20 if you have a oscilloscope and a battery. You can use the battery as your inputs and outputs, or your inputs, sorry, as your ones and zeros. Just connect it to the different leads of the battery. It doesn't matter the voltage, because these are nice fat transistors. They can take a lot of abuse. And you just need a bunch of alligator clips. You can buy those on Amazon or eBay or Digikey or Mouser. You know, any of the electronics places. Electronic Gold Mine is where I got these, and they were really cheap. They're on sale. And if you're really cool, you can hook the output up to a speaker, and you can get free heat. And it's just the energy of the ones and zeros that gives you free heat in your room. And that's that cool. I mean, it's just magnetic waves coming off of it, and it gives you free heat. It's like infrasound magnetic heat from a quantum computer. How cool is that? I'm done. Thank you for watching. This is Michael Ellis.